Start. Now, hello everyone. Now I am going to talk presentations on Raman spectroscopy, which is a important spectroscopy to analyze the compound and have a great role for a researcher to analyzing the compound and also compound group. So now the topic on which I will give a speech like as introductions, principle, instrumentation, also and application, advantage and disadvantage, and last is references. So now for introductions, first of all I want to tell you about the name of person who discovered the Raman effect, like as Chandrasekhar Venkata Raman. He is an Indian scientist and he is also become a first Indian scientist who got a Nobel Prize for Raman effect in 1930. And he was a Southern Indian born in November 17, 1888, and that is November 21, 1970. And he has 30 papers published, and his research area like as acoustic and optical field. He is also a Indian Journal of Physics editor. Now, first I telling about the effect of light, as well as we know what is the effect of light when it falls on a material. So I give us some figure to knowing about that phenomena. First of all, it is not possible that according to physics, not possible the effect of everything will be 100%. So I give some example to knowing by figure. When a light is falls on a material, then some part of light is come back in the same medium and same frequency, and this phenomena is known as reflection. And if some part of light is go from to media material surface to another medium with same frequency, and this phenomena is known as transmission. And some part of light goes into a material, into a surface, but can't come into another medium, then this phenomena is known as absorption. And the third and fourth, which is very important, on which the Raman effect is working, like as scattering. The light goes in a material and pass out to another medium with different frequency. So this is known as scattering. Now, what is the principle of scattering? When a laser light, we can say that visible light, falls on molecules, then the scattering of light is occurs, due to which there are different type of wavelength light is produced. If sometimes if the incident laser light energy have E naught, and if the reflected light, we can say that the scattering light have energy larger than to initial light, then this is known as Raman scattering. And also similar, if the energy of scattering light is smaller than to initial, then this both case is the Raman scattering, and this is the one case on which the energy is same, is known as ray line scattering light. Now, here we also give us some phenomena. When a light, it is a cubic cell on which we have a material. When a light goes and falls on a material, then some light is transmitted, and if the wavelength of scattering light is larger than, smaller than to the excited light, is known as anti-stop. In this case, it is called, for here the Therefore, the energy is larger than to initial light. It means that the wavelength is smaller than to initially light. So here, if the energy is larger, so wavelength is smaller. So this is known as anti-stop line, and this, if it is a opposite of this, then wavelength is larger than the wavelength of excited light. In this case, the energy is smaller to this, is known as stop line. And this is the case where the energy is same, is known as elasticity scattering, and this is also fluorescence when the wavelength of scattering light is equal wavelength of emission light. Here the experimental setup of Raman spectroscopy is given, where that is a laser, and this is the band pass filter, natural density of filter, and then mirror. When a light goes and falls on a band pass filter, then it's some special type of laser is passed out and falls on a density filter, and then it falls on a mirror. The position of mirror is 45 degree. Due to which, when the light is passed on a mirror, then it will be reflected from a 90 degree and falls on a sample. And this is a focus lens which focus of the laser to a sample. Then when a light falls on a sample, then it will be scattering occurs on a sample, due to which a light is generated, which is pass out from the camera lens and filter also, and go into a polychrometer, and then here is some phenomena. There are mirrors, and it will be detected by the computer what is the graph of the sample. Now here is also I take some example of O2, and here is Si silicon atoms between that in red color there is O, and in blue color it is a silicon. Here, when a light, this is the ground state, and this is like as energy and vibration, and this is the excited state. So when a light falls on a material and the atoms get some energy and go to an excited state and come back in the same state, and this is known as ray line scattering. Here is showing green and yellow colors and also red colors is known as a Raman effect. And this is also when a light is go from the ground state to the excited state and come back in a different state, which is the upper state of the ground state, and this is known as stop Raman line, Raman scattering. In this case, the energy of this light is smaller than energy of this light. So we can say that here is the gap is like as h omega k. So the energy of this is like as h, and omega minus omega k. Omega is the frequency. Yeah, we can say omega is the angular frequency of this light. And now here, if the atom of material is also in excited some energy state and get some more energy due to the laser and go back and go into excited state and come back smaller than to the initial state, like as from in starting it was in some energy state and come back in the ground state, and this is known as anti-stop line. It means that this light have this laser light, this light is like light have more than energy of this excited state light. So this is the phenomena of Raman scattering, and here also I show some graph. So this is the when light is green and yellow and red, and this is a 1 0 1 0. It is a like as Raman shift. And Raman shift, I want to also talking about the wavelength of the laser light. It is also important for analyzing our sample, because which types of laser, which wavelength of laser light we use in our system, it is also important. Here is also we use the 514.5 nanometer photon. The laser is used, due to which we use this. If we use different type of laser, our graph become shifted in some phenomena. Now here is also some graph of this, like that. This is the Raman scattering, that is a ray line scattering, and this is the anti-stock, and this is the stock. In this case, I just discuss about that. In this case, this is got from ground to excited and come back to some energy state. So it will be like as a stock line. That is a left side, and this is the when is some energy state and come back in the ground state. It go to its right side. So in this case, this is the anti-stock line, and this is the stock line, or this is the what I say, forget. Like as a stock Raman scattering. So now here is also I provide some phenomena, like as on which the Raman scattering is working. If our light is passed on a sample, then the element of that sample will be vibrate and have a different type of vibration, like as some rotational and vibrational, and third is rotational and vibration Raman spectra. So for first case, rotational Raman spectra. What is a rotational Raman spectra? When a light is falls on a metal, then the some compound of element have some only rotational vibration, rotational motion. So for that, here is also give us some phenomena on which we can say that which is the stock line and which is the anti-stock line. Here is a give a that is a delta Z is equal to 0, comma plus minus 1, and E is equal to, that is epsilon is equal to beta J plus ka 1. If the scattering, that is a Vs, the scattering frequency is equal to given as mu naught is the frequency of laser light, minus ka 4 beta J plus ka 6. In this case, the line is known as stock line. And this opposite, if the mu s is equal to mu naught plus ka 4 beta J plus ka 6, and in this case the scattering is known as anti-stock line. And for vibrational Raman spectra, here is some different, that is a delta mu is equal to 0, plus minus 1, plus minus 2, plus minus 3, and so on. And E is equal to is given as E, we can say that epsilon is equal to, it is a symbol of energy, mu plus ka half omega var E minus ka mu plus ka half square omega E or xe. So delta mu is equal to omega var E bracket में 1 minus का 2 xe centimeters inverse. So this is the frequency. If in this case, how can we say that which is the stock and which is the anti-stock line? If mu, that is a here like as a mu s, here is mu s is here is become to plus, not it become to minus, then it will be become stock line, and this is become to plus, and this is known as anti-stock line. So here I didn't write about that. So now rotational vibrational Raman spectra, In this case, that is the delta mu is equal to 0 plus minus 1 and delta j is equal to 0 plus minus 2. So here we got three branches, that is a O branch, Q branch and P branch. For about O branch, its delta mu is equal to plus minus 1 but delta j is equal to minus 2 is known as, in this case we can say that this is the O branch. And for that, delta mu is equal to plus minus 1 in three cases, delta mu is same. Only different is delta j. That is, here is j is equal to 0 is known as Q branch, if delta j is equal to plus 2 and is known as P branch. So now here is some Raman graph of node C. So here, like as when a light is it is showing my language, like as emission spectra of a water sample from the node C illuminate with the ultraviolet light at 270 nanometer wavelength. So it is a lot of portions of fluorescence. This is the portion of fluorescence, because in Raman spectra we have to see which is the fluorescence and which is the stock or anti-stock line. So and it is also given by the coloring. It is a wavelength is depends on as well as we know which color has which type of wavelength. So as we are increasing in this side, here is like the color change to blue to red, because the wavelength is 700 to change the 400 to 700. So this is a lot of fluorescence. Now here I'll give some applications of Raman spectra. Raman spectra is commonly used in chemistry since vibrational information is specific to the chemical bond symmetry molecules. Therefore, it provides a fingerprint by which the molecules can be identified. And also in solid state phase spontaneous, Raman spectra is your characterization material. Characterization material, measure temperature and find crystallography orientation of the sample. Raman spectra can be used to observe the low frequency excitations of solid such as plasmon, MOMOs and superconducting gap excitation. And Raman spectroscopy can be used in investigating the chemical compositions of physical diseases, also economic and conditions at the times of documentary were produced. And also Raman spectroscopy is being investigated as a means of details explosives for the airport security. In airport there are a lot of Raman's spectroscopy is used to detect the object which we are taking, so due to which we can analyze what things in your bag. Raman spectroscopy can be used in technical and identifications of the seafloor hydrothermals and the cold sea minerals, and it is also used to determine between the healthy and unhealthy tissues, because Raman spectra is also measured to measure the human body, which tumor, which tissues is good and which tissues is bad, which tissue is not working form. So we can also analyze for that. And it is used in medical field, like as it is used in medicine, aiming to development of the new therapeutic drug and in the diagnosis of the anterosclerosis and cancer. Advantage of Raman spectra. There are a lot of advantages of Raman spectra, like that. That is many organic and inorganic material can be measured by the Raman spectra, and also we can measure the group element, which types of group element is present in our sample. Two sample purification need. For that, if we want to go to a Raman spectra characterization, so we don't need to any extra preparations to characterizations of our sample, and no identified of water. We don't need to mix up any water of our sample. No destructive. So highly specific, like as a chemical fingerprint of material. It is a 98% is good for every compound to analyze that. Raman spectra are acquired quickly within a second. It is by the Raman spectra we can measure our sample in very quickly. Sample can be analyzed through the glass or polymer packaging. We can also, it means that there is no effect of polymers and also packaging. If we have something, then it can be measured. Laser light and Raman scattered light can be transmitted by the optical fiber over long distance for the remote analyze. And here is also main thing, the Raman spectra, the reason from 400 to, I hope this is a mistake. It is right. 400 to 50 centimeter can be covered by a single recording. Raman spectra can be collected from very small volume, and inorganic are easily analyzable with Raman spectroscopy. So but it has some also disadvantage of Raman, like as cannot be used for metal and alloy. It can be determined. It can be telling about for metals and alloys. And the Raman effect is very weak. It is very weak. The detections need a sensitive and highly optimized instrumentation. If we have some problem in our instrument, then the result will be not a good. Fluorescence of impurity or the sample itself can hide the Raman spectra. Some compounds fluorescence have irradiated by the laser beam. And sample heat through the intense laser radiations can distort the sample or cover the Raman spectra. So we have some problem also. So this is my references on which I read and I collect my data.